This call is now being recorded. Okay, once again, good afternoon, everyone. This subject is STAT, STAT 332, with the descriptive title Theory of Statistical Inference. This is a continuation of STAT 331, okay, Theory of Probability. I think I'm the one who handled STAT 331. I started discussing chapter 1 up to chapter 5 of the book of Statistical Inference by George Casella and Roger L. Berger. And I'm going to use this book also for our subject STAT 332. So we're going to start now on chapter 6, in which we have these principles of data reduction. Before I'm going to start, as a review, there are two major areas of statistics. We have the descriptive statistics, and then the other one, we have the statistical inference. So in descriptive statistics, review lang ito, it deals mainly with summary calculations like the mean, the variance, the standard deviation, and others. And then we have also the graphical and tabular displays of a given set of data. And we know that it focuses only on the given set of data, so it does not attempt to draw conclusions about anything that pertains to more than the data themselves. While in the area of statistical inference, it is concerned in making generalizations for the population based on the information gathered from the sample. In other words, it is concerned in making inferences for our unknown population parameter based on the information that we get from the sample. So this chapter 6, which is Principles of Data Reduction, is applicable especially if we have a large sample. Meaning to say the sample size of our sample is large. And we're going to apply these principles of data reduction. So an experimenter uses the information in the sample. We have these finite random variables, x sub 1 up to x sub n, to make inferences about an unknown population parameter. And we denote it by theta. So if the sample size, small n, is large, then the observed sample, we have here the realized value of the random variable x sub 1, we have small x sub 1, and so on and so forth. And the realized value of the random variable x sub n here is, we have here small x sub n. Will also be a long list of numbers that would be difficult to interpret, since we know that our sample size n is large. So what will the experimenter do? You might wish to summarize the information in the sample by determining a few key features in the sample values. And then this is usually done by computing statistics. We all know that a statistic is also a random variable, which is also a function of the sample. Say, sometimes we denote our sample, this sample, by this vector x. Meron siyang underline dyan. Ang ibig sabihin yan, bold yan siya na x. So in other words, it's a vector of random variables, having the random variables x sub 1 up to x sub n. So pwede ganito yung pagka-express ng ating sample, and so on and so forth. So we have a bold x here for our vector, and then we do not have a bold letter for a random variable. So we have a sample, and then this is the observed, the observed value of our sample. But sometimes it can also be uh, called simply as a sample. So dapat alam nyo kung kailan gagamitin yung observed sample o sample. Minsan yung observed sample, sample din yung pagkabasa niya. Okay? So we have a function of the sample. Say this function t, and then this is our sample, which is actually a vector of random variables. So ito yun. So an example of this statistic, we have the sample mean. So in this case, when we have a sample mean, yung t of x natin dito would be the summation of the x sub I, okay, over n, I from 1 up to n. Okay? The summation starts, or the index of the summation, I starts from 1 up to n. Hindi ko na lang naisulat yan. So we have a function of a sample, and this is the summation of the random variables x sub I. No, that's the value. Or rather, the random variable x sub I over n. Or you can have also the sample variance, which is also a function of the sample. Or we can consider the largest observation. That means that the t of x, the t of x would be the maximum. Kung largest observation natin, the t of x would be the maximum of all the random variable x sub I is for all I. Or you can consider also the smallest observation. So we have an example here for statistics, and this will be used to summarize some key features of the sample. So having a large sample size, then we can summarize our sample, and then we're going to use this to make inference for our unknown population parameter, and then we use the function of our sample. So we denote a bold-faced letters to denote a multiple variates. So ito yun. Denotes the random variables x sub 1 up to x sub n. Pwede din naman may parentheses, no? Yung ganun. And then the realized value of this vector is also a bold small letter x. So denotes the sample. Okay, ito yun yung kanyang mga sample, x sub 1 up to x sub n. I think you have encountered this in chapter 5. So any statistic, t of x. So t here is a function of our sample. So it defines now a data reduction or data summary. So an experimenter uses only the observed value of the statistic. Okay, this is the observed value of the statistic. This is our statistic. Okay, uses the observed value of the statistic rather than the entire observed sample, bold small x. So we treat as equal samples x of x and y that satisfy t of x is equal to t of y, even though the actual sample values may be different in some ways. Pwede din ito, no? Say, for this given observed sample, so the value of our statistic, t of this observed sample equal to this value, though these two samples, bold small x and bold small y, are different. So we use this only the value of our statistic. Okay, so we study three principles of data reduction. So we are interested in the methods of data reduction. Ano yung mga data reduction natin? Data reduction that do not discard important information. about the unknown parameter theta, and then methods that successfully discard information that is irrelevant as far as gaining the knowledge of theta is concerned. So we have the sufficiency principle. That's the first one. It promotes a method of data reduction that do not discard information about the unknown parameter theta while achieving some summarization of the data. Another method, we have the likelihood principle. It describes a function of a parameter, okay, determined by the observed sample. And this likelihood principle, the function of the parameter contains all the information about theta that is available from our sample. And then the last one, we have the equivariance principle. It prescribes yet another method of data reduction and still preserves some important features of the model. And we will see here in this method uh, what we call invariance uh, in our function, in our distribution also, or function or distribution. Okay, so we have three principles of data reduction. So the first one, we have the sufficiency principle. Ano itong sufficiency principle? So a sufficient statistic for a parameter theta is a statistic that in some sense or certain sense, it captures all the information about theta. Take note, all the information about theta contained in the sample. Any additional information in the sample beside the value of the sufficient statistic, it does not contain any more information about the parameter theta. Kasi nandun na lahat no, sa sufficient statistic ang mga information natin na kailangan about this unknown population parameter theta. So we have this sufficiency principle now that if T of X is a sufficient statistic for theta, take note, no? This is a vector. So T of the sample of random variables. So a sufficient statistic for our parameter theta. In this case, we simply have not bold theta. So somehow we will consider that we have only one parameter, sufficient statistic for parameter theta. Then any inference about the parameter theta should depend on the sample x only through the value of the statistic T of X. So that is if X, if we have sample points X and Y such that the function value or the observed value T of X is equal to T of Y, then the inference about the parameter theta should be the same, whether this random vector or this random variates, bold X is equal to the observed sample bold Y, or the bold sample X is equal to the bold small sample Y is observed. Say for example, we consider our statistic the sample mean. If we have a observed sample which is bold X here, say considering only that we have three random variables. So the first value of the random variable, say we have 4, next one we have 2, and then the next one we have 3. And then the realized value of our sample mean, so we have here T sub small x bar small x would be equal to the mean. So 4 plus 2 plus 3 divided by 3. So we have 6 plus 3, 9 divided by 3. So the answer is equal to 3. And then we have another sample point y, which is also a vector of values, say containing 3, 3, 3. Okay? So the t of y here is also equal to 3 plus 3 plus 3 divided by 3, and the answer is equal to 3. So the function value of this sample points uh, of our no, the sample value of our sufficient of our statistic t, uh, they are the same, then the inference about our parameter theta should be the same. Whether we're going to choose uh, the realized value of our sample to be bold small x, or you may consider the small bold y. Pareho lang pa rin yung inference natin ang makukuha about theta. Kahit saan dito yung gagamitin natin, whether the bold small x or the bold small y. So we have the formal definition now of a sufficient statistic. A statistic T of big X is a sufficient statistic for our parameter theta if the conditional distribution of the sample X given the value of the statistic T of X, it does not depend on the parameter theta. So we call this as the working definition uh, in showing that a particular statistic is a sufficient statistic if the conditional distribution of the sample X in other words, we have here, if the conditional distribution of our sample X equal to this small x here, mga bold yan siya, given, no? Given, baliktad. Dito pala sa taas yan. Nasa definition tayo. So dito, probability that this random variable or random variates x is equal to this observed sample small x given the value of our statistic, say equals to small t. And then, with respect to our parameter, no, theta, it does not depend on theta, so this conditional probability will be equal to 0. Or equivalently, we can have this expression, okay, given that t of the value of our statistic, pwedeng ganun, will be equal to 0. So theta here is the parameter of our sample bold x. So we have our working definition, and then to show if the statistic t is a sufficient statistic, then we must show that this conditional probability will be equal to 0. But this definition is being used to prove theorem 6.2.2, in which the theorem 6.2.2 will now be used to show whether a statistic t of x is a sufficient statistic for our parameter. So if we have here in theorem 6.2.2, if p of x given our parameter theta, so this is the joint PDF or PMF of our sample bold x, and then q of t still we have the same parameter. It is the PDF or PMF of the statistic t of x. Then t of x is a sufficient statistic for theta if for every observed sample point bold X in the sample space, the ratio, okay, this ratio, the joint PDF divided by the PDF of our statistic is constant as a function of theta. Okay? So, ito ngayon, sufficient statistic siya if this would be true. That it is constant as a function of theta, or it does not depend on our parameter theta. So let's have an example to illustrate this. Example 6.2.3, we have the binomial sufficient statistic. So we let the sample x sub 1 up to x sub n, the IID Bernoulli random variables with parameter theta, where theta is between 0 and 1 exclusive. Okay? So we have an IID random sample in which the x sub I here having a Bernoulli distribution with probability of success theta. We know that the PMF rather of this, say x sub I, we have here small x sub I, okay? Pwedeng ganun. Pwede din ganito yung kanyang pagka-express ng kanyang PMF. Okay? This would be equal to theta raised to x sub I 1 minus the probability of success raised to 1 minus x sub I, where the value of x sub I is either 0 or 1. Yan ang support niya, no? And then we have already this IAD. And then we will show that this sum of random variables, we have here the summation of the x sub I here. Ito. I from 1 up to n. We know the distribution of this sum of random variables having a Bernoulli distribution, having a binomial distribution. Yes, a binomial distribution with parameter, dito ko na yung sulat, no? N, and then the probability of success, theta. So, let's consider now the joint, rather the ratio of the PMFs. So we have here on the left-hand side the ratio of the PMF. So yung joint natin, supposedly, since they are IID, then it's actually a numerator natin would be the product, okay, the product of the probability, the PDF. So in this case, ito pala, ito, we denote it as P. Okay? Pwedeng ganun yung pagka-denote natin. P of x sub I given theta. Kasi ito yung P. P kasi siya, no? And then we have the sample, bold, x. So I from 1 up to n divided by yung PDF or yung PMF ng ating sufficient statistic. Eh, binomial naman yung sufficient statistic natin. Ito, binomial siya. There's a binomial. So ito yung kanyang PMF. Combination of n things taken t at a time, the probability of success raised to t, the probability of failure raised to n minus t. Okay, so we have that. And then yung ating joint, the product of the P. So we have here the product as a numerator natin. And then take note that we define our T here to be the summation of X sub I. So yung T of small x here would be equal to summation of the X sub I from 1 up to n, and we just let this to be equal to small t. Kaya ito. And then taking the joint PDF in our numerator, so we have the product here, the product of theta, then we have this in our numerator for our PDF. And this is for our denominator, the PMF rather, the PMF of our sufficient stat. And then simplifying, since the summation of X sub I is T, then we have this. And then this would cancel out. This will cancel out, as well as this. So we are left with this expression, 1 over combination of n things taken t at a time. Or simply, we have this expression. And we have seen that the ratio of PMFs does not depend on the parameter theta. Ngayon, wala na siyang parameter, yung ating ratio. Then we can conclude now that our T of X, this T of X, is a sufficient statistic for the probability of success theta. So the interpretation is this: the total number of ones in this Bernoulli sample, it contains all the information about theta that is in the data. Let's have another example to further clarify or illustrate the definition as well as the theorem 6.2.2. So we have the normal sufficient statistic. So we let X sub 1 up to X sub n be IID, normally distributed with mean mu and variance as sigma square, where sigma square is known. So if sigma square is known, the unknown parameter here is the population mean mu. So in this case, our theta, no? Kung tingnan natin, our theta here is actually the mean mu. That's our unknown parameter, theta, which is equal to mu. Now, we wish to show that the sample mean, this is X bar, will be a sufficient statistic for mu. Guess lang ito. This sample mean is just a guess. Na guess natin to be a sufficient statistic. We just guess it. No? Guess lang ito. It's just a guess. Gaya dito. Guess natin, we will show. We just guess that this statistic is a sufficient statistic. Say for example, ang ibibigay ko lang sa inyo, you have this random sample and then find a sufficient statistic for that. Find a sufficient statistic for our sample. So mag-guess kayo kung ano yung sufficient statistic natin sa ating sample. Itong case na to, normally distributed ang ating random sample, and we guess that the sample mean is a sufficient statistic for our population mean mu. So, considering now the joint distribution, so doon sa ating theorem, P yun siya, no? P. Ito P. Yung ating joint PDF or PMF of the sample. Pero pwede natin palitan as F. Kaya ito F. So the joint PDF of the sample is, we have that actually, no? This is equal to, numerator lang muna yung evaluate natin. So pwedeng ganito yung pagka-express natin, x sub 1 up to x sub n, given our parameter mu. Since this is IID, then we have the product of the probability density function. Pwede siya x lang, where x is normally distributed, or x sub 1, or any of that. Sabihin na x sub I na lang natin. Then we have here, pwede na hindi natin isulat yung ating subscript. Ano lang, small x sub I. Pwede na ito, no? Pwede ganito. Nandun yung random variable, nandun yung observed value niya, or simply just f of x. Parang ganun. And then we have the parameter. Okay? I from 1 up to n. So we have this. What's the PDF of our random variable x sub I? Normally distributed. So we have here 1 over the square root of 2 pi, then sigma, then e to the negative x sub I minus mu quantity square over 2 sigma square. Then we can express the 1 over square root of 2 pi times sigma as this. So raised to the negative 1/2, and then we put a sigma square inside our radical symbol. So that's the negative of 1/2. And then taking the product of all these PDFs, taking the product. So we have this, obviously, for our second equality. And then e to the, by using the law of exponents, e to the a times e to the b will just be equal to e to the a plus b. So we have here the exponential of the sum of this expression. Okay? And then we can simply add and subtract the sample mean, observed sample mean on this given expression. So ito yung result natin ngayon. We add and subtract. Okay? So if we're going to expand this, ito ng part na to, we're going to expand this, we have x sub I minus x bar quantity square, and then plus 2 times x sub I minus x sub bar, and x sub bar minus mu, and then plus x bar minus mu quantity square. So this would imply that if you're going to consider the summation now, so we have this summation. Now we have this summation. Yung sa second term, itong part na to. So we have the summation of 2 times x sub I minus x bar, and then x I from 1 up to n. So we can write the expressions that does not depend on the index of our summation before the summation symbol. So we have 2x bar minus mu. Then we have here the summation of x sub I minus x bar. I from 1 up to n. Since using the property, the summation of the deviations of every observation from the sample mean, we know that this is equal to 0. So the whole thing will be equal to 0. So yung second term pala dito sa summation natin will just be equal to 0. That is why what is left here, we have the first term here, ito, and then this last term. So we have here. And then the summation of this last term because it does not depend on the index of the summation. That is why we have n times the square of x bar minus me, and then over. Okay, so this is our joint PDF. Yung hanapin naman natin, ano naman yung distribution ng ating denominator, yung sufficient stat na sample mean. We know this already in nasa chapter 5, no? No, I think nasa chapter 5 that the distribution of the sample mean is also normally distributed with mean equal to the population mean mu, and the variance is equal to sigma square over n. Kaya ito, we have this. So ito yung kanyang, sa denominator, ito yung kanyang probability density function. Ito yung nakuha natin sa numerator natin. Nakuha natin kanina dito sa 6.2.1. Ito na part. And then, just using the law of exponents here, no? Ito yung law of exponents, e to the a, and then, e to the b will just be equal to e to the sum, a plus b. Ito yung gagamitin natin in simplifying this ratio of PDFs. For example, ito. Ito, at saka ito. Pwede natin ilabas yung ating denominator na n to the negative 1/2. Ito na yan. So yung maiiwan na lang, ang hindi magkapareho. Ito, at saka ito na lang. So the negative n over 2, and then minus 1/2. Okay, so we have these results. And then sa ating exponential function, no, sa exponential function natin, in that case, not necessarily e, no? Pwede din naman ito na x to the a, x to the b, x to the a plus b. Yan yung sa una natin ginamit. Ito yung sa e na part. Excuse me for a while. Okay, guys, let me continue. Sorry for that interruption. Now we see that the ratio of the PDFs does not depend on the parameter mu. So kung titingnan niyo dyan sa last na expression, wala na yung mu. Therefore, the sample mean is a sufficient statistic for mu. So given our random sample having a normal distribution with mean mu and variance sigma square, where the variance is known, and then we guess that the sample mean as a sufficient statistic. So we have verified that indeed the sample mean is a sufficient statistic based on the theorem 6.2.2. Any questions or clarifications?
None, sir.
Okay, thank you for that, Marivic. So
Sir,
yes, Nolly?
sir, ang sufficient statistic ba, sir, kay unique?
No, it's not unique. No, it's not unique. You can have many sufficient statistic for a given sample. Now we're going to proceed to theorem 6.2.6. We have the factorization theorem. So we're going to use this theorem now to determine the sufficient statistic. Hindi na natin kailangan mag-guess pa given a random sample. So hindi na natin kailangan mag-guess kung ano yung sufficient statistic natin dito. But using this factorization theorem, it will give us the sufficient statistic. Okay? So let F, now we have here the joint PDF or PMF of the sample. And then a statistic T of X is a sufficient statistic for the parameter theta if and only if there exists a function G sub T of theta and H of X such that for all sample points, bold X, bold small x, and all parameter points, the joint PDF can be expressed as the product of these two functions. So the first one is just a function of the sample, while the other one is the function. No, it's a function of our sufficient statistic of our statistic T of X given our parameter theta. In our theorem here, we have the assumption. We have this assumption that a statistic T of X is a sufficient statistic if and only if there exists a function. Rather, we have a biconditional statement here. Now, biconditional statement that if statistic T of X is a sufficient statistic for the parameter, then it can be expressed, yung ating joint as the product of these two functions. If the product of these two functions, if we can express the PDF, the joint PDF as the product of the two functions, then it would also imply that our statistic T of X is a sufficient statistic. Excuse me muna, inom muna ako ng tubig. Okay, let's have example 6.2.7, a continuation of example 6.2.4. We have here, yung sa example 6.2.4, we have seen that the sample mean is a sufficient statistic for our sample. We have this as our joint PDF. Nakuha natin yan. We see that in in 6.2.1, ito yung naka-express na PDF. 2 pi sigma square raised to the negative n over 2. We have the e exponential of this summation of xi minus x bar plus n times x bar minus mu quantity square. Okay. I from 1 up to n here. And then we divide this by 2 sigma square. So E of the sum could be expressed as the product of this, no? Product of these exponential functions. Ito yung first. Okay, so we can define our h of x. Ito yung h of x. This is a function of our sample, of the observed sample, no? Bold x. Wala naman dyan yung mu. And then we know that our sigma here is known. So this is just a function of x. So ang remaining expression dito, ito, you have this, would be the function g of t, and then mu. So considering t here as our sample mean, this one. Hence, we have expressed the joint PDF of our sample as the product of these two functions. So the t of x here is a function of the sample. This is the function of the sample natin. No? It's a function t of the sample, small bold x, is equal to x bar. So this would further imply that our statistic, t of bold x, we have here x bar. So ito yung t of x natin, t of small x, we have here. And therefore, by factorization theorem, the sample mean is a sufficient statistic for V. Diba yung sa example natin kanina, sa example 6.2.4, we just guess the sample mean as the sufficient statistic. Itong example natin ngayon, using factorization theorem, hindi tayo nag-guess kung ano yung ating sufficient statistic, but based on the joint PDF of the sample, we were able to obtain the corresponding sufficient statistic for our sample. Okay, guys? So, mas madali, no? Gamitin yung factorization theorem. Let's have another example. We have the uniform sufficient statistic. We let x sub 1 up to x sub n be IID observations from a discrete uniform distribution on 1 up to theta. So that is the unknown parameter theta here is a positive integer, and the PMF of our random variable x sub I is this. So ito yung kanyang PMF. No? Given our parameter theta. So this 1 over theta, x, the value or the support for this, 1, 2 up to theta, and then 0 otherwise. Or we can write this using the indicator function as simply, no? 1 over theta, and then you have the indicator function on this set 1, 2, up to theta. So we have here x. Pwedeng ganun. So using the factorization theorem, the joint PDF of this random sample, okay, ito should be equal to the product of f of x sub I given the parameter I from 1 up to n. Okay, that's by definition. And then since IID, no, since IID, then we have this value now. Theta to the negative n, x sub I from 1 up to theta for I 1 up to n, and then 0 otherwise. Okay, or this could be expressed. No? This could be expressed as, dito ko na isulat, no? Equals, yan. This could be expressed as theta to the negative n. We have here x sub I is an element of 1, okay, and so on and so forth. Is for I 1 up to n. And then we have an additional na ang maximum, the maximum of the x sub I for all I is less than theta. So yung value nito mga x sub I natin should be less than theta. And then 0 otherwise. Okay, pwedeng ganun yung pagka-express natin. So the restriction that x sub I from 1 up to theta, okay, could be expressed for I 1 up to n can be re-expressed as x sub I element of this. Okay, so there's no theta in this restriction, but we have an additional condition here that the maximum of the x sub I should be less than theta. So we define na ito, the maximum of the x sub I as the value of t of the sample mold x. So we consider h of x here, which is just a function of the sample. Malitong form niya, it should be h of x na bold, okay? In that case. So we have that. And then we're going to consider, pwede siya ma-separate, no? So ang theta to the negative n, nawala na yung theta dito. It does not depend on the parameter theta because of this fact, no? May theta man dyan. Theta to the negative n, so 1. So dito natin inilagay yung theta to the negative n. So 1 dito sa kabila for the h of x, na 0 otherwise. We consider t as the maximum of the x sub I to be less than or equal to infinity, and then 0 otherwise. So we have factored, our joint, our joint PMF. Now we have factored a joint PMF as the product of these two functions. So ito yung g, ito yung h of x. So yan. H of x, oh, sorry. Ito yung h of x, ito yung g of t. So yung t natin dyan, which is equal to the maximum of x sub I. So the largest order statistic here is the sufficient statistic for this problem. So hindi tayo nag-guess, but based on our factorization theorem, we're able to obtain our sufficient statistic. So this type of analysis can sometimes be carried out more clearly and concisely using the indicator function. Okay, so we let this script n here as this script n as this set 1, 2, and so on and so forth, set of positive integers, and the script n sub theta will be this given set. So using the joint PMF, ito, yung joint PMF would be the product of this. And using our indicator function, ito na ngayon. Babalikan natin na yung kanina. Ito, ginawa natin ito, equal siya sa script n. Script n of theta. So parang 1 of theta I, then you have script n of theta, and then you have here x. That's your PDF of the random variable x sub 1 or x. So ang joint niya, ito na ngayon. The product of that. 1 over theta, this theta to the negative 1. Ito yun. Then simplifying, we have this. And then we can consider again t of x. So express natin itong n of theta here as a big N, script big N, and then we can have also this product of that. So this is now a function. No? The first factor here is a function that depends on the sample. And then this is now a function that depends on the sample, on the value of the sample given our parameter theta on the second factor. So that is why the maximum order stat, maximum exabyte is the sufficient statistic for theta. So pwede ganito yung pagka-solve nyo. Pwedeng maggamit ng indicator function or pwede yung say task. So in our example, the first 3 examples that we have a sample of random variables. No, we have a vector of random variables, and we just consider only a parameter, only one parameter for our theta. But it could possibly be a vector of parameters. So yung theta natin, pwede siyang vector of parameters. That is why we have now a bold, we have now a bold theta. We have a vector of parameters, theta sub 1 up to theta sub s. Theta sub s. And still our sample bold x here from x sub 1 up to x sub n. Then we can have a vector. Meron tayong tawag na vector of statistics. Ito ngayon. We have a vector of statistics. T of bold x. So hindi lang isa lang pala, pwede para yung sufficient statistic natin, it is a vector, no? It's a vector of statistics. So this situation often occurs when the parameter is also a vector. Say for example, meron tayong ngayon, no? Example, we have a sample here, IID, normally distributed, but in this case, we have 2 unknown parameters. We have mu and then sigma square. So, ibig sabihin yung vector, bold vector theta natin, parameter theta natin, ito is equal to the vector of unknown parameters, mu and then sigma square. Okay, so given this sample, normally distributed with mean mu and variance sigma square, both mu and sigma square are unknown, how are we going to determine the sufficient statistic? So in this case, our sufficient statistic would also be a vector. So based on our factorization theorem, so hanapin muna natin yung ating joint PDF ng ating sample. Ito man yun. Diba? We have this. So the joint PDF of our sample. Yan. Naisulat ko kanina from 6.2.1. We have that. So it depends on the sample. Observed sample ito. Observe of the observed sample, small bold x only through the values of t sub 1 of x equal to the sample mean, then t sub 2 of x to be the sample variance, in which we have this. So, ibig sabihin, itong part na to, ito, no? This can be expressed as n minus 1. Then you have here the summation of x sub I minus x bar n minus 1. Okay. So, we have n minus 1, no? N minus 1 times s squared, because this is the summation of this expression here is s squared. Yeah, ito, s squared. But we let it as the value of this, no? Observed value of t sub 2 of the sample. We denote it as t sub 2. Kaya n sub 1, t sub 2. Then ito ngayon, the sample mean. So the t sub 1 here, t sub 1 sample mean equal to that, t sub 1. So we have factored, no? Na-factor natin ang ating PDF, the joint PDF, as a function of the sample only, h of x, and the function of our statistics, given our parameter mu and sigma. So in this case, in which we have a vector of parameters mu and then sigma square, then our sufficient statistic is also a vector of vector of statistics. Ito siya. We have now this vector x bar and s square as a sufficient statistic for mu and sigma square in this normal model. Okay? Any questions or clarifications? So in example 6.2.9, it demonstrates that for a normal model, the common practice of summarizing a data set by reporting only the sample mean and variance is justified. If the sample mean and the sample variance is a sufficient statistic, so they all contain all the information about our unknown parameter mu and sigma square. That is why ito lang kailangan natin, just to summarize our data. Kasi they contain all the information regarding our unknown population parameter. So it is easy to find the sufficient statistic for an exponential family of distributions using the factorization theorem. Ngayon, ginamit natin yung factorization theorem to be able to determine our sufficient stat. But if we have an exponential family of distributions, we can also determine the sufficient statistic using factorization theorem. So we have here theorem 6.2.10. So we have a sample x sub 1 up to x sub n IID from a PDF. Yung PDF niya that belongs to an exponential family. When we say the PDF belongs to an exponential family, if the PDF can be expressed as this product of these functions. This is just a function of x. This is a function of the parameter. And then exponential, the summation, the finite summation of the function of the parameter, and then a function of x. This time, our parameter theta is bold. So pwede siya ma-apply even if we have a vector of parameters. That's why we have here p sub 1, theta sub 1, theta sub 2, theta sub d. Yung index ng summation natin, I from 1 up to k. So in other words, meron tayong k terms dito. And then the number of unknown parameters that we have, d should be less than or equal to k. Then, the sufficient statistic now, according to this theorem, is also a vector of statistics. So we have the summation of t sub 1, x sub 1. Now, x sub j, j from 1 up to n, and so on and so forth, is a sufficient statistic for theta. Ito, hindi siya nagbigay ng example. Dumiretso na kaagad siya sa definition ng minimal sufficient statistic. But I'm going to give you an example illustrating this theorem 6.2.10. So, kaya merong malaking space dyan. Wala ito sa book, but let's have this example. Kunwari, ito pa rin ang ating sample. IID, normally distributed with mean mu and sigma square. This would also answer to the question of Nolly a while ago. So where both mu and sigma square are unknown. Okay, so the vector parameter here, we have yan. Okay, take note. Hindi ito joint. Hindi ito joint PDF. But this is just the PDF of the random variable x. Since we know that the x sub 1 up to x sub n are IID observations. So yun lang yung the probability density function or the probability mass function of the random variable x. So kung normally distributed siya, ano yung kanyang PDF? Ano yung kanyang PDF? So this is now our parameter. No? Pwede natin specify ganun. We have mu and then sigma square. Kung gusto natin isulat yung ating, or simply just the vector bold theta. So what do we have? 1 over the square root of 2 pi, then sigma, and then e, exponential of the negative of x minus mu, quantity square over 2 sigma square. Pwede naman natin din na isulat yung x here from negative infinity to positive infinity because the support is actually all the real numbers. Kasi pag hindi siya ganito, kunyari, consider lang tayo ng positive, you must have the support of your random variable. So this could be expressed as 2 pi sigma square raised to the negative 1/2. So we have here the exponential of, say we're going to expand it, the negative x squared, pala muna, minus 2x mu, and then plus mu square over 2 sigma square. Okay, hindi ko na isulat yung ating support ng x because it's from negative infinity to positive infinity. So we have here 2 pi sigma square is to the negative 1/2. Okay, so pwede natin using the law of exponents, pwede natin mailabas yung exponential of the negative mu square over 2 sigma square. So yung maiiwan na lang sa exponential function natin, we have the negative 1 over 2 sigma square, then x square, and then plus 2 mu over 2 sigma square x. Simply, we can have 2 pi sigma square raised to the negative 1/2 exponential 2 sigma square. So ito, negative 1 over 2 sigma square x square, then plus mu over sigma square x. So kung makita nyo dito, a function of our parameter, sorry, lumampas. A function of our parameter, summation of that. So ito yung mga parameters natin. Ito, ayan, okay? So ang k dyan, 2. K is 2. And then a function of the sample. Function of the sample. Ano yung function of the sample? Orange tayo. Ayan. So ito ngayon. Function of the sample. So ibig sabihin ngayon, yung sufficient statistic natin, according to our theorem here, it's the summation. So dito ko na lang sulat blue na lang, para makita ko yan. So this implies, dito ko na lang sulat, this implies that T of our sample X, according to that, we have what? A vector of, we have the summation, no? Tingnan natin, we have the summation. Ano yung T sub 1 of the sample X sub G? X square dito, di ba? Sa baba, makita nyo? Ito, X square.
Yes, sir.
So we have now the summation of X sub I square. And then, I natin is from 1 up to n. And then the other one, K natin, 2 raman. So meron tayong K is equal to 2. So the summation, dalawa lang. What is the other one? P sub K of X sub G. X lang to dito. So big X lang. The same problem that we have a while ago, yung sample mean at saka yung sample variance, no, this vector of statistic is a sufficient statistic of our unknown parameter mu and sigma square. But we have also another sufficient statistic for mu and sigma square. And we have this. Hindi lang yung sample mean, but we have the sum of the square of the x sub I and the sum of x sub I. This is also a sufficient statistic for mu and sigma square. Hence, yung ating sufficient statistic is not unique given a sample. Did you get it, Noli? Meron ng concrete example?
Yes, sir. Thank you, sir.
So if we have a lot of sufficient statistics, what would be the minimal sufficient statistic? And that will be my discussion tomorrow. Okay? Any questions or clarifications? None so far?
None,
4
sir.
times a week ang klase, sir.
Yeah. 4 times a week, Monday, Tuesday, Thursday, Friday. Actually, so before, book lang talaga yung diretso, no? Yung discussion ko. Ito, do actually, kinuha ko sa book. Pero, pinik ko lang yung mga importante na part and I'm going to discuss it further. And for those examples or for those definitions or theorems that do not have example, I provide an example just like this theorem.
Sir,
Okay,
hanggang
so-
anong chapter po yung makover natin?
Nakalimutan ko, hindi ko nakita. Pero hanggang confidence interval tayo. Let me check. Six, 7, 8, 9. 6, 7, 8, 9.
Okay po.
Okay, so that's all for this afternoon. So hoping to see you tomorrow. Okay, so I'm going to stop now the recording.